Okay, and that is now doing what it should be. Excellent. So, rump kernels. What are these things? They provide production quality kernel drivers as components. So things, in this case, drivers are a slightly more general term, so it's not just a device driver, but anything that's like kind of like a protocol translator. So even your POSIX system calls are essentially a protocol which your applications use, and a network stack and so on. Development of rump kernels started around 2007 as part of the NetBSD project. And they use the any kernel architecture of NetBSD. I'm not going to go into great detail into that. What that basically means is essentially you can repurpose an existing monolithic kernel and turn it into a bunch of components that you can pick and choose from more or less independently. The Rumprun Unikernel is the actual software stack and also a command line tool, as you'll see, for building and running unmodified POSIX apps as unikernels. The initial support for Zen, which is what turned into Rumprun, actually got committed as rump user Zen almost exactly 2 years ago today. Since then, we now support Zen, KVM, bare metal on x86, x86 64, and ARM support just went in last week. And there's a link to Antti Kanti's excellent article, which has lots of history and detail. So, hello world. So the first non-trivial program which ran on Zen as a rump kernel-based unikernel was Netcat. And if you want to run it today, this is what you do. Basically, you run GCC, compile Netcat, then you run something called rumpbake, and then you, as root, rumprun your unikernel, and you'll see it boot, and then it will just sit there, which is what Netcat normally does. It just sits there and waits for you to send it something. I'll note that the rumprun syntax is under development, subject to change. So you connect to it from somewhere else, and the unikernel gets your packet, and it prints hello world, and then you send it an EOF, so it all just shuts down. Just like Netcat would do as a normal process. So what did we just do? We took an existing POSIX application that the latest Netcat version is apparently vintage 2011, but I suspect there haven't been very many changes to Netcat over the years since it came out. We cross-compiled it into a unikernel using the cross toolchain, and then we baked the final image using rumpbake, told it to do that for a Zen PV platform. And then we booted that on as a Zen DOM-U, and we sent it a packet, and it shut down again. So if we look at this binary, we can see that it's actually quite big, or the final rump-baked binary is. The actual size of that you can see is about 4.7 megs. That's quite big. So why is it so big? Embarrassingly big. What's in here? It's a very high-level overview of what actually goes into a Rumprun unikernel. So all of this stuff is running in a single thread, single address space. Starting from the bottom, there's something we call the bare metal kernel, which provides you platform bootstrap, scheduler, device access, small stuff. Then there's a hypercall implementation, which is what the rump kernel components interface to. That provides interfaces for basically malloc-free, some host I/O kind of thing, clock, console, threads, synchronization primitives. That's it. That's enough to get the rump kernel components running on anything, in fact. So not very many calls. So there's also a NetBSD libc, and then there's some Rumprun config and compat integration code, and at the very top is your application. Now, the important part of this is that the vast majority of this is all unmodified NetBSD code, and the vast majority. Yeah, so this basically just goes over some of the more details about what's provided in there. So the rump kernel components provide your system calls, network stack, file systems, device drivers, and the C and C++ standard libraries we have, so we can even run C++ runtime. That was quite an adventure getting that working. There's pthreads. It's mostly a POSIX interface, but there are some things that are a bit different. So we provide a cooperative thread scheduler rather than a preemptive one because it's just dead simple and very easy to reason about. And for the Zen platform, the bottom bit, so the bare metal kernel in there, actually contains the remains of Minios. Now, we used to use much more of Minios, but we've basically been killing as much of it as we can. Partly also because we want to unify the different targets that we have. So the Zen, KVM, bare metal use common layers. So what we're basically using today from Minios is mostly just some bootstrap codes, event channel handling, and the PV front-end drivers. It turns out that this is enough to run most things out of the box. Our toolchain provides what looks basically like a standard cross compiler. How many of you have used cross compilers? You know what the issues are involved? Okay, quite a few. Excellent. Okay, so we have out of the box support for autoconf, CMake, plainmake. We don't do shared libraries or dynamic linking. That kind of comes out of the definition of a unikernel in the single address space. We could fake it. It gets a bit complicated, but we may need to do that for things that depend on it. So there's a bunch of things like Python, Ruby, so I'm very used to loading dynamic modules all over the place. And because we'd like to run them unmodified, we may go down that way. So the rumpbake tool is used to, what your cross-compiler toolchain outputs is basically a relocatable pseudo-linked binary. The rumpbake tool is then used to say which components you actually want to go in there. So the definition of the rumpbake configuration, the Zen PV configuration in there looks something like this. And each of these are another set of actual static library archives that go in. For Netcat, we can just trivially throw out a bunch of stuff that we don't need. Netcat doesn't need any disks, doesn't need random numbers, and so on and so forth. So if we rebake Netcat with that minimal configuration, we can see that the size goes down by a decent chunk. It's still big, but we haven't really tried too hard to make it smaller. When I was doing this slide, I sent it to Antti, and it was like, okay, I'll go and look, why is there so much BSS in there? Oh, scheduler.c has 256 CPUs statically defined in it, so that's about 600K or something. So we have a package repository called Rumprun packages, vaguely inspired by BSD package source. It's just a bunch of make files. It's a really, really good way to get involved. The goal is that you should just be able to run make and a unikernel of your favorite software package falls out. There's a small list of packages. The significant ones there in italics is what I'm going to demonstrate today. And that's Nginx, MySQL, and PHP. Most of the things that we've had to do to make software work, 99% of it has been fighting with build systems. So this is a message to upstream developers. If you want your software to run as Unikernels, or at least as Rumprun Unikernels, please, please, please make it cross-compile. And I guess a lot of embedded folks will be happy as well. And yeah, a good source of patches that can very often be just lifted is the build root project. Right. So, if you want to serve a static website with Nginx, then you clone Rumprun packages, you cd into Nginx, and you look at it, and there's a bunch of directories. You put some static files in images/data/wibble, and edit your Nginx conf, run make, and run rumpmake, and then run your Unikernel. What that command does is it runs the Unikernel with 128 megs of memory and 2 block devices mounted in 2 different places, one at etc for some stub files, which libc expects, and one with your data. And it adds a network interface. Now, what I'll actually show you here is, hopefully this won't break the synchronization between the 2 windows again. I've got a demo running here which you can happily poke at. It's just a Unikernel. So, right. And in fact, if we look in there, then there's our root directory. That's what it looks like. So there's kind of like a fake root file system, minimal root file system running in here. And we look in here, here's our Nginx configuration, which I wanted to point out, but I can't quite see. I should have brought my mouse. Where's the nginx.conf? Sorry?
Third one.
That one?
Third one.
So it looks something like this, very minimized. And the interesting points there is only one worker process because, well, we don't have processes. And the master process has been switched off, but it all just works fine. This is because we don't do fork. We could do fork, but we also don't do virtual memory. It's kind of by design and keeping things simple. But it actually works fine. I did ask the Nginx guys if there was any problem with running Nginx that way, but apparently not. So the network configuration, you have 2 options. The first one is basically the back-end configuration that gets passed to the XL tool stack. So that says we actually want to create a network interface for this DOM-U. And the second option, which matches up with the first option through the tag, tells the Rumprun Unikernel code how you want that interface actually configured. So you can do static IPv4, IPv4 DHCP, or IPv6 stateless auto-configuration at the moment, which is great for spawning lots and lots of Unikernels. The block device configuration looks something like this, and it basically give it a path where you have your block device or image file, and then a mount point if you want one. Otherwise, you just get a block device. And we have file system support for FFS, CD9660, ext2, or whatever else is in NetBSD. The reason we're using image files for a lot of stuff is they're really easy to work with, recreate. Also, using ISO images is just a way of saying, well, this data really is read-only and you can't touch it at all. Of course, we could just make the file read-only in the DOM not. I guess that would work. But we could use LVM volumes, but you need a bit more infrastructure for that, because often what you want to do is update your data and reboot the Unikernel. So what can you do to deploy these things? Well, it turns out that you can just run -i and feed it to a pipe. And this happens to work well with systemd, or you could pipe it to logger. This configuration is one that I'm using in fact, for that demo that I just showed. And there's nothing particularly special about this. It's just a systemd unit. What I found is I also added in a script that gets run when you restart it, which automatically regenerates the image file if I've touched any of the files the Unikernel needs. That's useful. Yeah, so the options for logging, yeah, your application can just output to standard error. That goes to the console. You can pipe that to somewhere. It turns out there's a couple of Zen console bugs I found along the way, which have actually been patched, and the patches are in 4.6 for some really simple things where you couldn't actually pipe XL console to something that wasn't a TTY. There's also another one which is a bit more annoying, which I've not looked at, which is if your Unikernel exits really quickly, then you lose a bunch of messages because there's a race condition somewhere in the Zen console D stuff and you don't see half the messages. You can just stick sleep before you exit. The other option for logging is to use a remote syslog server, which actually works really well with Nginx because it just has baked-in support for that. So you can just stick a management network, another network interface on your Unikernels and have a syslog server on there. And there's a little snippet of rsyslog configuration, which looks a little bit like line noise, but what that does is split up your logs into based on the host name of the Unikernels that sent them, which is useful. So the other half of deployment which is important is what do you do for monitoring and vital statistics? Things like memory usage, are your file systems inside the Unikernel filling up if you're writing to them? We don't have a good answer for this at the moment. The easiest approach is you could just print stuff periodically on the console. I've got some code for that, but the accounting of who is responsible for what and the memory allocator is not quite there yet. So it's not ready to actually commit. The other interesting alternative for monitoring is to use something called Sis Proxy, which is a mechanism that Rumprun have built in, and it lets you basically do client server where you have something running, say, on your DOM naught, you have essentially a recompiled binary of netstat, which actually calls system calls over some transport in a kernel that's somewhere else. That would let us use unmodified NetBSD tools to inspect a running kernel. So interesting things to do there. Okay, so the ramp stack. So what are one of the big milestones or the original goals when I started working on Rumprun was that I really wanted to have PHP running as a Unikernel because I don't trust any PHP application. And so one of those targets was Roundcube webmail because I already run that, and so it was an obvious thing to, yes, please, let's run this as a Unikernel. So we have the ramp stack, the Rumprun answer to MySQL and PHP. It's an Nginx Unikernel which serves your HTTP or HTTPS on your front end. It speaks fast CGI to the back end, which is a PHP Unikernel running your PHP application. Again, we don't have fork. The normal setup for this on normal Linux system would be you fork off multiple PHP processes so that you can serve requests concurrently, while you can just run multiple Unikernels. And the last component is MySQL Unikernel, which PHP talks to. Now, this is literally millions of lines of existing production code. So Nginx is about 100,000. PHP is about 850K. MySQL is about 1.7 million lines of code. And there's no modifications to any of this code to make it work apart from the build systems. So I've packaged up Roundcube webmail and Rumprun packages as a package, and if you want to run it, then again, I'm really trying to make things as simple as possible here. So you just need to build your Nginx PHP MySQL packages, and then you need to edit a bunch of configuration files and run scripts to map your network configuration to how the back ends of the Unikernels are supposed to communicate. I'll get to that. And point it to an IMAP and SMTP server it can talk to, run make, and then you run 3 scripts, which you can find in the Rumprun packages GitHub repo, which is just run something or other. And you end up with something like this. So you've got Nginx talking to the internet over its Zenith naught internally. And then we have it bridged to PHP, MySQL, a log host, and a normal Linux DOMU running IMAP and SMTP. This is kind of the simplest configuration I could come up with, but all the different DOMUs can talk to each other, so it's not ideal. Because what I'd like to have is a situation where Nginx can only talk to PHP, PHP can only talk to MySQL and to the IMAP server. But there's no such thing as a point-to-point link in Zen networking. So you could do it with routed networking, but then you haven't really won much and you still need to write all the firewalls on the DOM naught. You could do it with separate bridges. I tried that, and it just gets horrible to manage in practice. So, not really. So the answer to that is, I think, to use vChan, which is a mechanism that Zen provides for basically fast inter-domain communication using shared memory between DOMUs. And that's a major goal that I'd like to get to be able to use that easily. In a similar way to linking containers with Docker, basically. That's the kind of the user experience I want to get to. I just want to say, please link Nginx to PHP and PHP to MySQL. So, what are the other security implications of Rumprun Unikernels? I think there are Unikernels in general and are a good alternative to containers. You've got your much stronger isolation guarantees. You've got a much smaller TCB to deal with. And with the vChan links, for example, PHP doesn't even necessarily need a TCP stack at all. It just needs something that looks like a Unix socket to PHP, or an INET socket, but it doesn't actually need to be implemented as TCP. It can just go straight into vChan. And as you saw briefly in the Nginx demo, it's a very minimalist approach. So the Unikernel doesn't have a shell, and all of its program data is generally read-only. So even if you were to exploit it, well, I mean, your standard shellcode exploits aren't going to do anything useful because exec bin sh is just going to say, go away. Enosis. But even then, there's not a hell of a lot that you can do to actually get a permanent foothold in a system like this. I'm not claiming that that's a security breakthrough, but I think there's an interesting space there in thinking about how we can lock that down even more. So the aspect of unikernels having a static code base, we could do interesting things there with, for example, having a hypercall in Zen to say, I'm not going to map any more executable pages ever. Please don't give me any. Yeah, so I think it's an exercise in minimalism. I like minimalism, and all unikernels are essentially an exercise in minimalism. And containers are getting better, but it seems to be a little bit of people are trying to slim it down gradually, rather here we're starting with nothing and just adding in the bits that we need. So challenges and future directions. So I've talked about the vChan, Unix to vChan shim a bit. That also gives us an interesting ability to do things like replace the Nginx component with a Mirage unikernel serving TLS. Now, what that does is it gives you an answer to, Heartbleed, for example. I want to run a completely different TLS stack, but I don't necessarily understand OCaml, and I want to run my PHP application using this TLS stack. So that's a nice way to give people choice in the technologies that they want to use. We also want some kind of solution for, well, nicer solution for file access or data access than ISO images. So I had a discussion with Anil about this yesterday, and he sort of said, "Well, nah, you don't want to do NFS, and you don't want to run the file system in another domain than the application that's using it." So I'm sort of going a bit back and forth on that, but we need something. I don't know what that is yet. We definitely need to improve debugging, logging, and monitoring. Debugging is hard at the moment in the sense that you can't easily just introspect the unikernel and tweak things, and running GDBSX on it is not an answer for normal mortals. It seems to work, but it also seems to be one of those pieces of the Zen tree which no one's touched in years, and there's all sorts of strange misbehaviors that I found, and some very obvious low-hanging things like, why do I have to run XL pause in another console instead of just pressing Control-C in GDB? In fact, if I press Control-C in GDB, it just hangs. EC2 support, which is being worked on. So the idea is, it's an obvious target. The EC2 interfaces are weird, but we have actually managed to get Rumprun Unikernels booting on EC2. We'd just like to automate it in a way that makes it accessible to anyone who wants to try it. And yeah, more software, more languages. You know, that's a great way for people to get involved. So, we can run unmodified POSIX apps, existing applications, as unikernels. The applications I've shown are not particularly special. They're just applications that I needed. And I think the project's mature enough at this point where people who aren't necessarily systems people can get involved. We're a friendly community. We have a mailing list. We have an IRC channel. We won't chase you away if you ask silly questions, so please do. And yeah, it's a bit shorter than I thought it was, so that's good because I think there'll be more questions, I hope. So please ask questions. Ooh. No questions? Yeah? Sure. Yes.
So for Rumprun, basically you pick kernel components that are needed for the application.
Yes?
How do you determine the exact components that you need for a particular application?
Well, in the default configurations, you just get everything we have. So you don't need to worry about it from a user point of view unless you want to start slimming it down. And then how you determine that, it's a case of, you know, does my application need block devices? Can it run out of an in-memory file system? If you've got something like, say you're building a key store application that you want to run as a small unikernel, it probably doesn't need a block device unless you're storing millions of keys. Don't know. In that case, you wouldn't need all the VFS code, or most of the VFS code in the file system code. Same goes for the network stack. So you can pick and choose the bits of the network stack you want. Don't want Unix sockets, just leave them out. Don't want IPv6, leave it out. Don't want IPv4, leave it out.
So we should be aware of which, like, so whom do you expect to actually, generally the persons, the developers who develop applications might not have a perspective into what kernel components they might need.
They don't need to.
But if they want to slim it down.
If they want to slim it down, they can, and the end result is the image that you boot, right? The unikernel. It's not. It's the source of. It's self-contained, right? So if your developers build smaller unikernels without components, then your ops people can just run them, right?
But the process could be automated, right? Because you have the dependency information in the build system, so you could do some analysis and try to eliminate things automatically.
Yep.
Okay. It just hasn't been done yet.
Yep.
There's no reason why not.
Okay.
Yes? Yeah?
Yeah, something technical.
Sure.
Because I'm curious. The thing with the single address space and support, is this coming from this layer that you have underneath that you based on MinOS?
The BMK stuff.
Exactly. Or is it just because you don't compile in the, let's say?
Well, the rump kernel code doesn't do any of the scheduling. That's part of the hypercall interface that it calls when it wants you to schedule, right? So that's not its decision. The rump kernel components, how you implement the hypercalls, that's up to you. So it is a result of the fact that the BMK bit, the bare metal kernel bit, doesn't do address space bit switching. But then that's also something we don't want that because it's complicated and it's also slow. Yeah, so, yeah.
It's not to be useful or not.
Yeah.
It's just something that's curious.
Yeah. Yes?
So this runs in ring 0 on x86?
Yes, but it runs in ring 0 as its own VM. Yeah. So in a virtualized ring 0. What we're actually doing at the moment on Zen is PV, but the Rumprun Unikernel actually has support for KVM and bare metal, so the commands are almost the same. You just say rump bake hdub hardware virt.io, and then you can run it directly under KVM. And you could also run it under Zen as an HVM domain, but we haven't really bothered with that. Yes?
Another thing you made regarding the drivers. You said you use the netfront, the blockfront from EMS.
Mm-hmm.
Couldn't you use the netfront, blockfront? I don't know if there's something in NetBSD like
Yes, we could. We just haven't gotten around to doing it.
Okay. So you did the same thing. Right?
Yeah, and it would probably run better. I mean, the Minios netfront driver is pretty sucky. That was one of the first things I fixed last year back in November when I first got a web server running, and I loaded the hell out of it, and it just stopped processing packets. And it turns out that the ring in the Minios netfront just filled up and everything just stopped. So yeah, we could replace that with the NetBSD drivers. We'll probably get around to it at some stage. It's pretty easy to write additional rump kernel components to talk to things like a netfront driver. And so you can kind of pick and choose there easily. If something hasn't been done, it's just because we haven't gotten around to doing it.
Okay. Fair enough.
Incidentally, I think it was back in April that I did some very basic performance tests just using something like Siege to load up Nginx and compared on the same hardware to a NetBSD current DOM-U and a Debian Jessie DOM-U, and the completely unoptimized Rumprun stack using the Minios driver actually performed a little bit better than the NetBSD DOM-U, and it was, I don't know, 30% slower than the Linux code. But then, as I said, this has not been optimized in any way. Any more questions? Yes, sir.
Have you tried like passing? Can you pass physical network interface to the network?
Yes, you can, and we have support for that in the Zen and in the KVM builds. So you can actually reuse. In that case, you use the unmodified NetBSD driver for your device. Yeah.
So you tried the performance test in that? That's interesting.
No.
What did you pass through?
Yeah, but mainly because the main Zen box I'm using at the moment, I'd have to go and wander into a data center and hook up extra networks to it. So. Yeah. Anyone else? Okay, well, thanks to everyone for listening, and please try it out and report back.